Hear me? Nice to meet you all. Right. Okay. So my name's Sam Martin. I am. What am I? I'm a fellow at Arm. I work in Central Technology, which is a group in Arm that worry about our GPU roadmap. So we own the technology for our GPU roadmap. And about 5 years ago, we started on a journey to consider what we should do to bring ML and graphics together. And so this is the motivation for this talk. That's why we're here 5 years on, trying to announce the things that we've done and what we think needs to happen in GPUs, APIs, everything surrounding them, in order to keep pace with the kind of change that we see coming. So sometimes you do get moments that just upend everything. And ML or AI, we use the term ML inside Arm, but same thing. They tend to come around upend everything. And this creates a lot of disruption, but it also creates a lot of opportunity. And you can see this really clearly at SIGGRAPH. If you've been coming to SIGGRAPH for a while, you'll have seen that all the talks at SIGGRAPH for a long period of time have been almost slowly replacing the state-of-the-art with some ML-based state-of-the-art. Way back in, let's say 2020, you go to talk and it'd be talk after talk about how the, previously really carefully handcrafted state-of-the-art algorithm had been replaced by a unit or something similar, right? So we've been seeing this for a long while, and need to ask ourselves now, well, with this kind of scale of change, what should happen to hardware? What should happen to software to allow us to support the opportunities that are coming along? Now, the way we look at this, and I should say, first of all, we're looking at this for ML in real-time graphics, right, which we call neural graphics. So there's lots of uses of ML in graphics, offline, content creation, all sorts of things, but specifically about real-time use cases of ML on graphics in particular. How do we try and look forward at what the kind of change that we might see? And we bracket this between a kind of conservative view, which we're really comfortable with, absolutely going to happen, dead certain, and on the upper end, a bold view, like the most outrageous things that we could contemplate seeing. And the conservative view, I think, is quite straightforward. Because we've already seen great examples of this today. Neural supersampling, which you might see examples of like NVIDIA's DLSS, are already having a massive impact on graphics today. They are really transformative for graphics efficiency. And so we are at least going to see significant change from that technology alone. And we're also going to see, in graphics more broadly, ML on what I might call full-scale images, something that requires ML on a 1080p image, being a major feature of most, if not all, image processing applications. And so this kind of really conservative view of it, the bit that I don't really speculate, I don't think it's too speculative is going to happen. This already is going to be a huge amount of change and is going to demand us to adapt, to accommodate it. But the bold view is very alive and well at SIGGRAPH. And we've had, great talks like Marco Salvi talking about which parts of the GPU pipeline will we see replaced or displaced or augmented by ML in the future. And this is still very much an open question. Right? Like, will we see neural materials completely replace we do rendering? Will we see some neural post-processing? And it's a great example of that just there that I've not even seen before. Come in and change radically the way that we're doing things. And, and perhaps it's not even so bold to suggest that ML will be the technology that underpins entirely new kinds of imaging applications that we've just not seen before. So somewhere between those two extremes is where real life lies. But we also ask, well, what would happen when deployment of neural graphics networks is an open thing, right? Where anybody can just go and train their own neural graphics network, develop their own thing for their own application, and have a viable means of deploying it cross-platform, cross-vendor at scale. Like, that is something that's not really possible today, and that's what really needs shaking up. And for that, we need new hardware, we need new APIs, we need new tooling, and we have to expand the industry expertise so that everyone's in a position to go and do this kind of work, to take this kind of opportunity. So that's our goal. We see an open ecosystem as an objective for our work. But there are lots of GPUs. Like in Android alone, we saw 25 new GPUs released over the last 10 years. And if we get this wrong, there's potential for significant fragmentation, and that will hold everyone and everything back. Right? So we think it's really quite important that we as an industry find a way to allow this open development of neural graphics applications. And that is in mind in our, in everything that we do. So our vision for this, and the topic for today's talk, is the hardware, the APIs, the tools, the shared expertise that we all need to bring, and that Arm are contributing and publishing today to help bring this GPU vision. But we're Arm and we make like power efficient designs. So we're looking at 1 watt and upwards mobile GPUs, right? How do we do this? Not just on giant servers, massive desktop machines. So how do we do this on a mobile GPU in a way that also scales up to other platforms? Something that scales across this range. So we need an open platform for neural graphics that starts at mobile and scales up. So I'm going to start with neural supersampling as the backbone for this. This is like a core part of this conservative view we spoke about, and we call it neural supersampling, or NSS. Now, why is it so good? Right? Well, it enables really high upscaling ratios, fundamentally. So our kind of go-to resolution for this, at least for mobile, is 2 by 2 upscaling. So we render a quarter of the pixels, and we upscale it, by 2 by 2 in each direction. That's, imagining 3/4 of all of the pixels. But we're not actually really imagining them, we're reconstructing them. Neural supersampling is closer to temporal anti-aliasing with upscaling. It's a reconstruction algorithm, not a static image upscaling algorithm. So there's no kind of hallucination in here. It's pure reconstruction. And if you're reconstructing 3/4 of the pixels, you can expect to get on reasonably complicated content something like a 2x speed up. Though this will be massively content dependent, right? You're not going to get 2x speed up by upscaling Angry Birds. Then you won't get a 4x speed up either, because you've still got your vertex processing and there's other bits that don't get scaled. But if you're under a quarter of your pixels, like 2x upscaling is 2x performance improvement is the kind of thing you should expect. And that is really enabled by this ML network. Because if you've ever mucked around with temporal anti-aliasing, you realize, it's great, but there's all these corner cases where all this ghosting happens, where I get all these weird effects, and this grass doesn't work, but then the character's okay, and you end up tweaking it per bit of content, per character, right? All of that tweaking, all those kind of heuristics that you're effectively typing into your code, that's basically what you're training the network to do, right? The network is learning all of those heuristics. So it's a classical reconstruction algorithm at heart, but it's learning all the content-dependent tricks, nuances that need to be applied in order to get the right results for the right content. And that's where the magic comes in. Right? That is why it's magical. But in order to do that, there is a minimum viable network size, right? A minimum viable network that has to be run at a reasonable rate. Otherwise, you just won't get the benefits, right? And I'm going to come back to exactly what that criteria looks like. So if we're going to talk about this, we're going to need a network. Last year at SIGGRAPH, Liam O'Neill, who I think was here and has just run away, there he is, and colleagues, worked on a neural supersampling algorithm. We spoke about it in the Moving Mobile Graphics course last year. Slides are online. We've updated those slides and we've republished it. It's on Hugging Face right now. You can go and download it. And our motivation for doing this is not to kind of keep a neural supersampling algorithm to ourselves. It's to build a reasonable industry baseline. Like no other upscaler should be worse than the one we're just publishing today. Otherwise, you may as well just pick up the one that we've got, right? But we're publishing it so that people can take it, fork it, build upon it, modify it, customize it, do what you want with it. So there is a good baseline. So this is our offering to start this. And I'm going to show a video. So this is an in-house demo we built. On the left is the demo rendered at 1080p with anti-aliasing, as you might normally. And the right-hand side, we're actually rendering at 540p, upscaling to 1080p, so 25% of the pixels up to 100% with our NSS algorithm. And basically, it's imperceivable, right? If you zoom right into it, you will see differences, right? We are only rendering a quarter of the pixels. But from a, like an experience point of view, this matters because the right-hand side is half the cost of the left-hand side. And I can tell you that there's no other hardware feature today available or on our roadmap that would deliver a 2x performance increase overnight. Right? That's just unheard of levels of. So this technology really is quite transformational. Now, if I'm going to dig into this a little bit, right? Here's a frame of the Enchanted Castle demo. I can lay up the ground truth, so that's 1080p rendering with anti-aliasing on the left, and the next column along is ARM Super Resolution, ASR. ASR is derived from AMD's FSR2. The same quality as it, there's various different optimization points, but it's like a mobile optimized version of FSR2. So ASR and FSR are really the state-of-the-art in non-neural upsampling. And they're great algorithms, right? You should go and pick them up and use them in titles, shipping today. But that's kind of where the state-of-the-art in non-neural upsampling gets to. And then we have DLSS2 and NSS, which, I would say that NSS is, approaching competitive with DLSS2. We use DLSS2 as a good measure of good enough, right? Like DLSS2 has been adopted by games. It is being seen as as the point at which this becomes viable. And so there will always be some gap to the ground truth, but this is an absolutely usable technique, but available on mobile. So some key facts about NSS. First, we can tell you from experience that you're going to need a network that's about 10 GOPS, like 10 giga operations per inference. That's the kind of order of magnitude we're talking about. You can make it larger, but if you try and make it much smaller than that, it won't function as well. You start just losing fidelity, right? Like that's kind of like your minimum viable point. Also, if you try and figure out, well, how fast do I need this thing to run? Well, if I'm looking at a 60 hertz application, I'm going to need it to be less than 4 milliseconds. So I'm going to say, well, why 4 milliseconds? Well, if my frame took, say, 14 milliseconds, then I'm going to get a 2x speed up, say, so it comes down to that. If I add on more than 4 milliseconds, I won't see anything more than a 25% uplift. Now, if I don't get much of a more than a 25% uplift, I might go, well, why am I bothering, right? So 4 milliseconds for 60 hertz, that's this is agnostic of any technique, any resolution, any GPU, anything, right? This is just true just from, like, basic arithmetic. And so anything lower than that, and it's kind of not worth it. Now, our network that we built is kind of equal parts compute and ML. And so actually the ML part of that is going to have to work in half that budget, and ideally significantly less than that budget. Plus, sustainable power on a GPU on a mobile phone is about a watt. It can consume significantly more than that, but if you want to be gaming for a long period of time, you're talking a watt. And so you can just kind of join these things together. Well, I'm going to need a 10 TOPS per watt per second accelerator. And if I'm going to use this, I need high utilization out of that as well. I can't just massively underutilize or anything. That tells us that we need an NPU class accelerator in mobile. Other platforms will be able to do things in different ways, but for mobile, that's our logical conclusion that we get to from starting from these really basic assumptions. So in GPUs, shipping now to our vendors, but coming shortly, we will be seeing NPU class hardware embedded inside the GPU. We're adding what we call neural accelerators into every shader core. They're high efficiency, high throughput. We're not saying anything about performance at this point. We're not saying the kind of configurations that people will build. That's all to come. But these accelerators are coming. And it is a dispatched size accelerator. That's kind of the way it's exposed to the system. It looks and smells like a compute shader. You dispatch it like a compute shader. It synchronizes like a compute shader. It accesses also memory as a compute shader. It is part of the GPU. You can mix and match it with compute. So all the scheduling, control, memory access, that's all basically the same. That's why it's important, because you need this as part of the GPU. But it isn't a simple MATML accelerator. It operates on whole tensors. It needs an ISA, so like a virtual ISA to describe the operations for it. And this kind of formulation delivers the performance that's necessary to do things like NSS. Now you might ask, well, why didn't we go with extending the execution engine on the left-hand side of this with a MATML accelerator? And the basic thing is that we won't get the perfs per watt that we need in order to deliver this. There are things that you can do if you have a bulk accelerator that you cannot do if you just make a simple shader extension. So for mobile, to achieve these kind of things, this is the architecture that we believe we need. But of course, we need an API to drive it. And so we've been working for some time now in Kronos, where we're big proponents of standard APIs. We work a lot with the Kronos community, and we've made proposals for ML extensions to Vulkan. There's a collection of them. The main one is called data graph pipelines. The key observation is that we do need a whole tensor ISA. Now, that's outside of graphics. This is what you'll see for any kind of ML work whatsoever. There's a whole ton of whole tensor ISAs floating around the world. We're building on a standardized one called TOSA, Tensor Operator Set Architecture. And essentially, we lift it into SPIR-V. Right? So there's a SPIR-V extension. They're called SPIR-V TOSA. Otherwise, the API is kind of how you might imagine if you had that in a compute shader. First you export some SPIR-V TOSA from your upstream tooling. We'll get to it a bit later. You can load it, compile it to form a pipeline, and then you can dispatch it like a compute shader. If you can synchronize it with other compute shaders, you can share data with other compute shaders. And so it's just like a compute shader dispatch, but it operates on whole tensors, which is that necessary thing that we need in order to get the speed up that we need in mobile. And this should be supportable cross-vendor, and we're working with Kronos to see the standardization through. It's dispatch level acceleration is our goal. Now, it's no good just having hardware and software. We need to enable people to build on top of this. And so today we're also releasing a neural graphics development kit. And there's a large collection of things that I'm not going to be able to talk through in details in this talk that we're shipping. But I'll start with the game engine plugins. So we have a straightforward plugin for Unreal that includes NSS. So today you can go and download plugin for Unreal and run NSS. But of course, hardware isn't shipping today, so we have an emulation layer for this that runs on desktop GPUs. So you can see, it is a bitwise accurate emulation layer. So you can see exactly what you'll get in future hardware when it comes down. So you can go and play with that in Unreal today. Of course, we're shipping the NSS as a model. This is available on Hugging Face, has a source for all the shaders, has all of the weights. It has a training flow. It has a data schema, so you can create your own. If you wish, you can create your own data for it and retrain your networks on it. It has what else was that? I'm forgetting all the things that we're shipping now. But there's a large collection of things and how-tos, sample code, documentation, tooling for this, all available. And I think a good place to start would be to look at Hugging Face and a landing page there. There's a model card up for it. You can go and explore and download all the assets. NSS is, for us, just the beginning. As I say, our goal is not to become model vendors. Right? We want to enable other people to go and build these techniques themselves. But this is new technology. We need to show a good baseline for this. So we're shipping NSS today, but in-house we have neural frame rate upsampling. This basically does frame doubling. So given 2 frames, you can interpolate the frame in the middle, frame insertion. This is great, and we'll be putting it out shortly. And then we have a variation of NSS called neural supersampling and denoising, NSSD. This is for upscaling and denoising ray-traced lighting. And so we'll talk about it again in the future, but you can take super noisy ray-traced images and upscale and denoise them. This is something that we think is really quite interesting coming in these future generations, because the combination of better ray-tracing hardware, and there's been many years now of generations of improved ray-tracing hardware, getting to the point where it's really going to be quite decent in the coming years, combined with the ability to do neural denoising and upscaling. These things, are coming at almost the same time, and really reflect I think they're like I can't even think of the word right now. Inflection point. That's what I'm looking for. Inflection point, where you suddenly become possible to do fully ray-traced lighting and denoising on mobile in real time. And we know this is possible. We are built in-house. We have this today. So this is, we are really close to this becoming a viable thing. Anyway, we'll be publishing these networks as openly as we can in time. So here we are. Right? This is how we believe GPUs need to adapt to the age of AI, and how we need to enable neural graphics at scale. We have our hardware. We have the APIs. We believe are cross-vendor supportable. We have a ton of tools, networks, etc., to equip and power developers. And we're already working with a whole bunch of partners behind the scenes to have content for this of this hardware when it first ships. And we would love to continue working with others. This is probably the largest ecosystem enablement program that ARM have ever considered doing. It's such a transformation, and so we'd love to come and work with anybody else and come and talk to you. We have a room here at SIGGRAPH. We're over in the East Building, room 10, first floor, head to the far back left corner. Just wander in, come and see us. We're here all week. We're obviously around. Come and talk to us whenever you like. There's another talk from us later today on exactly this stage at 2 o'clock from Peter Hodges over there, talking about all of our ecosystem things. We're also talking about ray tracing over in the workshop over there. Jose Emilio is going to be doing something on Thursday at a time I can't remember. Sometime I can't remember, but it's on Thursday. I'm sure you can look it up. Thank you very much.